Hello again. In this video, we're going to continue on with our understanding and work on something called electron arrangements. In the last video, we talked about Aufbau principle and electron configurations. In this video, we're going to look at the next type of electron arrangement, and that's called an orbital diagram or an orbital filling diagram. Orbital diagrams, a little bit more of a diagram than just a shorthand code like an electron configuration. As you know, very, very compact. 1s2, 2s2, and so forth. Just a few characters that tell us a lot of information about an atom's electrons and how they're behaving, where we would find them in terms of their energy levels and the shape of the region that they occupy. But an orbital diagram shows us just a bit more information. It does take a little bit more space to write. It's a little bit more of a diagram than just a bunch of letters, but it's a little bit more informative in some really important ways. Orbital diagrams show us each of the electrons in its orbital. Each electron of the atom in its orbital. And an orbital is part of a sublevel, so we're going to look at that today a little more closely as well. Orbital diagrams also allow us to observe how Hunds Rule is applied. And we haven't talked about Hunds Rule yet, but it's coming in the video here in just a minute or two. It also, orbital diagrams allow us to sort of continue to show the Aufbau principle, because as we draw an orbital diagram, we draw each sublevel, 1s, 2s, 2p, 3s, and so forth. We draw each of those slightly higher than the last, almost like a gradual staircase, which helps us to model the Aufbau principle, or sort of remind us that Aufbau is still in play, and there's still that rule. The electrons will be in their lowest energy positions available before they go on and fill in higher ones. So just to remind you, we've been talking about this colorful periodic table with these different sublevels, with these different letters and numbers in different places, and hopefully you've gotten pretty comfortable with the pattern that the periodic table has in this way. We're going to look a little bit more closely as we look into these today. We're going to look a little bit more closely at each of these sections. So 1s, 2s, 2p. We're going to look at those in terms of their orbitals and how the electrons actually behave. So within 1s, there are 2 electrons found at the most. Within 2s, there are 2 electrons found at the most. Within 2p, there are 6 electrons found at the most. How do those 6 electrons sort of coexist in the 2p sublevel? How do the 10 electrons potentially here exist in the 3D sublevel? How do these things rectify with the different numbers that we're seeing? And so here are what orbitals look like. The bad news is orbitals are very complex. The good news is you don't have to draw these. Really, I shouldn't say that. You don't have to draw anything beyond the first 2 rows. So if you can draw a circle, like you see in that first one, and understand the idea of a sphere, which is what that S orbital is meant to represent. And if you can remember the idea of a figure 8, or sort of an hourglass. We've described it as an hourglass, or even as a dumbbell. And some people, I think in the picture version, it looks kind of like 2 sides of a doorknob on 2 sides of a door. These orange and yellow ones in the p orbitals, these are our figure 8 shaped or our hourglass shaped, dumbbell shaped orbitals. And then beyond that, you see they get more and more complicated. In the D, they're kind of those 4-leaf clover lobes. And then in the F, they look like a big bunch of green grapes or something, and we get more and more complicated shapes. So as we're going, you don't need to worry about drawing these as much as you need to understand when we refer to them why there are, for example, 3 p orbitals, why there are 5 d orbitals, and why there are 7 f orbitals in a set, in a sublevel set. So because these are very messy to draw, and they have this geometric orientation that you can kind of see, they're all drawn centered on an X, Y, Z axis, like you might learn about in your math class. Because there's a lot to drawing these and shading and so forth, we aren't going to draw them like this. But what these represent are the regions of probability in which we sort of predict or expect that we would find the electrons in those sublevels most of the time. Those 3 p orbitals here in this set represent the areas around a nucleus where we would expect to find those 6 2p electrons in an atom like neon, or an atom like magnesium that we did in the last video. 2p6, where are those 6 electrons? Well, specifically, there are 2 in this first sublevel orbital, so there'd be an electron sort of moving in one direction here and in the other. Now that's way simplified. In reality, the electrons they don't really move in the way that we expect to describe them as moving. But when we detect them or find them, we find them in these regions of probability that are drawn in this color. So it's as if you drew a bunch of dots. If you're familiar with art and pointillism in art, if you take a bunch of dots and just draw in a bunch of dots, they eventually would make the shapes that you're seeing here. And if we were to take 1,000,000 pictures, or so to speak, of an electron in an atom, we might find that those million pictures add up to sort of represent these regions of probability. And that's still not getting the whole story across, but that's kind of what we're looking for here. So what sort of idea is that we have 2 electrons that are whipping around in here. So I have one electron that's zimming around in here this way, perhaps. And it makes this kind of a shape. And again, that's sort of simplifying it so we can talk about it. And then we have another electron that's whizzing around in here in the other direction, sort of moving in that shape. So 2 electrons can occupy this funky geometry. One sort of moving in one direction and one moving in the other. 2 electrons can kind of occupy this funky geometry here. And 2 electrons can occupy this geometry here. So that's a total of 6 electrons. That's why we say that this is, if this were 2p6, that 2p6 with its 6 electrons, right, is actually occupying 3 different sort of geometric regions. 2p6's 6 electrons are found in these 3 different sort of geometric orientations. One of them, as you kind of see here, and I'm just going to clean it out again, one of them is lying in this x-axis, the way that this is drawn. One of them is lying in the z-plane, or the z-axis, as it's drawn here. And then one of them is, one pair is lying in the y-axis. And again, that's 2 electrons in each of those axes, right? So I'll draw on the second one. So in the x and the y and the z axes, there are 2 electrons in each of those positions for a total of 6. And we can do the same thing down here in all the others. Okay? It doesn't matter how many lobes you see, those funky ones with 4 lobes, or down at the bottoms, the ones you see that have 8 lobes. There's still just 2 electrons in here. So I can imagine that this is 2 electrons sort of moving in this orientation, maybe 2 electrons moving in this orientation, and you get the idea, and so forth and so on. More and more of these orientational directions. And then this one here that looks kind of like some sort of funky, I don't know, wormhole or something. I'm not sure where I would draw the electrons exactly in there, but there'd be 2 electrons in there too, okay, moving somewhere within that orientation. Each of those 2 electrons then, that adds up to a total of 10. 2 electrons in each of those orientations. And again, you don't need to draw those orientations. I'm going to show you, these are called orbitals. These funky color lobes that you're seeing here are called orbitals. I'm going to show you how to draw an orbital in a much simpler way. So this is what we would call one orbital. This is one orbital. This is one, and this is one. So if this was 3d10, let's say we were working with an atom of, if we were working with an atom of, yesterday we saw in the last video, selenium, that has electrons in the 3d10. The 3d10 sublevel is made up of 5 d orbitals. 5 separate d orbitals. And you kind of see here on these pictures that they're each labeled as D. D, 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 and D. Okay. So those 5d orbitals that each have 2 electrons in them, 2 electrons each for a total of 10. So 5 orbitals times 2 electrons each makes 10. On the previous one, 2p6, this is the 2p sublevel that has 3 separate orbitals, 3 p orbitals. And we say they're p orbitals because they're figure 8 shaped. 2 electrons each equals 6 total electrons. So these are p orbitals, and I have 3 of them. These are d orbitals, and I have 5 of them. And then on this bottom one, you can see there are 7 f orbitals. 7 f orbitals. And in a set then, each of those would have 2 electrons for a total of 14. I won't go through and try to draw all those in there, but there are 14 electrons in, we would say here, 7 orbitals. So it's important to recognize the difference between a sublevel, which would be all 3 of these p orbitals. This is a sublevel like 2p or 3p. An orbital is one single part of that, so that's this little guy right here. And then the sublevel includes several orbitals, 3 or 5 or 7 in this case. So there's kind of a lot going on in there, and as we practice these, hopefully it'll make more and more sense. Okay, so but we don't want to draw all this geometry, so we're going to take those funky shapes and we're going to sort of draw them a little bit differently. See all these fun shapes here that we just saw drawn out here? We're going to simply take those pictures away and we're just going to draw, this is how we draw our orbitals. So instead of drawing all those funky lobes and geometries, I just make a little set of spaces. Here's a set then, this is a set of 3 p orbitals. And when we say they're p orbitals, remember that's just because they have that figure 8 shape. This is a set of 5 d orbitals. And you can call them D-shaped, but they're not shaped like a D. They're just shaped like a clover leaf, which is what we define as D, right? So 3 p orbitals. This is a set of 7 what we would call f orbitals, which have that really complex kind of multi-lobed shape. Okay. And then this is a single s orbital. And the s orbitals are excessively simple compared to the others because there's just one of them. I shouldn't say orbitals because there's just one there. Okay. So this would be the 1s sublevel drawn as a single orbital. This would be the 2p sublevel drawn as a set of 3 orbitals. This would be the, on the left, the 3d sublevel drawn as a set of 5 d-shaped orbitals. And then on the bottom we'd have the 4f sublevel drawn as a set of 7 f orbitals. All these different shapes that we take away and just draw as little boxes. And that's much, much easier. All of us can draw these. Not all of us, myself included, could draw those orbitals from those previous pictures very effectively, very cleanly, and usefully. This way we can put electrons in those spaces. Okay. So to show 2 electrons in there, I would just show 2 arrows pointing up and down. To show 6 electrons in the 2p, I would just put 2 electrons in each of those, moving up and down. Remember how we drew in those arrows on that last one? 2 electrons moving sort of in opposite directions within that set of yellowish-orange lobes. And now we just draw the orbitals as little spaces with 2 arrows pointing in opposite directions. Here are 10 electrons in those 5 orbitals. 5 orbitals, 2 electrons each, total of 10. Pointing up and down those electrons, kind of opposite, balancing each other out. And then the last one down here in those 7 f orbitals, each of them could include up to 2 electrons. And if they're all full, then we'd have 14 electrons in there drawn as these little arrows. Okay. So it's as simple as that, little orbital diagrams drawn that way. Now, one of the things before we get into some examples that was mentioned before is that an orbital diagram allows us to see Hund's Rule being applied. An orbital diagram, or orbital filling diagram, follows Hund's Rule. And it's the first place that we see it. Hund's Rule says that no orbital, and that's one of those little spaces, right? Each of those little blanks is an orbital, not the set, but each of those little blanks. No orbital can include 2 electrons until every other orbital of equal energy includes 1 electron. So in other words, no one gets 2 until everybody gets 1. That's a really kind of fair rule if you're sharing a pizza or cookies or something like that. I can't have a second slice of pizza until everyone else has had a slice first. Well, in the world of electrons, when we have orbitals in a set, okay, orbitals in a set, you can't put 2 electrons into an orbital unless everybody else has 1 electron in it first. And this isn't our rule. We're saying, hey, electrons, you have to follow our rule. Hund's Rule is how we explain the behavior of electrons that we see, that we detect in electrons, in orbitals. And there's a lot of sense that's made of this, actually, when we get to things like molecular geometry, especially at the level of an AP chemistry class. So when I teach my AP chemistry class, we come back to and we use the idea of Hund's Rule in a lot more intimate detail. There's a lot of things that we observe in molecular geometries and hybridization and all kinds of cool things in AP chemistry that all act as evidence to support our understanding of Hund's Rule. So I hope many of you will take AP chemistry and I'll have a chance to get into this with you more. It's quite fascinating, actually, I think. So Hund's Rule, what does this mean? It means, again, like I said, that each of the 3p orbitals in a set, or each of the 5d orbitals in a set, or each of the 7f orbitals in a set, each of those orbitals gets 1 electron before any of them gets 2. Everybody gets 1 before anybody gets seconds. Okay, what does that look like to us then? So for example, Hund's Rule, if I was filling up and drawing a picture to show 2p3, so 2p3 on the left there, that doesn't work. 2p3, this isn't going to be okay. I can't draw 2p3 like that with 3 electrons in it because, look, that first orbital got 2 electrons here, 1, 2. But this last orbital doesn't have 1. And because they're all in the same set, they're all of equal energy. And that's what that phrase means, orbital of equal energy. That means they're going to be in one of these bracketed sets. If everybody didn't get 1, then nobody can have 2. So this first orbital has 2 electrons in it. And that means he's got a second one here before this last orbital had 1 at all. And so that's not okay. We need to balance. Everybody gets 1, and then if there are extra electrons are still remaining left over, then we can go through and put the second one in wherever we've got space until we run out. Okay? So 2p3 couldn't be drawn like that. This is not okay. And 3d6, we can't draw it like this because look, we've got 2 vacant orbitals over here that have nothing, while these first 3 each have 2 already. So imagine if you were out with 4 friends and there were 6 slices of pizza in this pizza. It's kind of a weird pizza, but let's just go with it. And 3 people each grabbed 2 slices and left 2 of you with nothing. Now, if you were one of those 3 people, you might be perfectly satisfied because you got pizza. But those 2 people that got none are going to be ticked, right? What happens if we have 6 slices of pizza and 5 people? Everybody gets one, right? And then the 6th one you got to have a battle for in some way. Maybe you do rock, paper, scissors. Maybe you'd slice it into smaller pieces and you all share it. Because you can do that with pizza. You cannot split electrons that way, so that wouldn't work. The 6th one would just kind of go to whatever orbital you'd want to put it in, and you couldn't be wrong at that point as long as everybody got one. Okay? In the world of pizza, maybe it's whoever house it is, or whoever picked it up gets the 6th piece, or whoever chipped in an extra $1, or I don't know, whatever the bet might be. Okay? This is okay. This is how we would draw 2p3 because we spread them out evenly. 1 in each orbital, that's fair and balanced. 3d6, 1 in each orbital, and then the extra one got put in right here. That's okay. That's fair and balanced. It's the best you can do. Now you might look at it and say, well, wait, that one got 2 and the other ones didn't. Hey, you can put it wherever you want. If you wanted to draw that one over here instead, that would be okay. If you wanted to draw it over here instead, that would be okay. You can put that 6th one wherever you want because you don't have enough electrons to go around for everybody to get to. You're doing the best you can, and that's all that we can expect of you when drawing an orbital diagram, is to be as fair as you can be. In truth, in reality, what we would actually observe is that 6th electron would sort of move between all 5 of the orbitals with time in an atom that had these electrons. So in an atom that has 3d6, and I believe that's iron, if I'm thinking right about it, an element like iron that has 3d6 at the end of its electron configuration, that 6th electron is actually detected in all 6, or rather all 5 of the orbitals at different moments. And what that sort of tells us and helps us understand is that iron's electrons aren't fixed. They're not like stuck onto the atom. They're moving around at random within that cloud all the time. And so they're moving between orbitals. They're taking their turns. They're jumping around and bouncing around. And all of the orbitals would sort of have an equal number of electrons with time. It would almost sort of average out. Okay. Again, more on that as we talk about an AP Chem, but for us, that's good enough. Okay. So let's look at an example. If we did an orbital filling diagram for carbon, with its configuration that we've got as carbon, 1s2, 2s2, 2p2. Right? That's its electron configuration from our last video. But for its orbital diagram, we would draw 1s2 like that. There's my 2s electrons, or my 2 1s electrons. There's 1s2. You don't need to write the 2 down there, but you can kind of use it to remind you that there are 2 electrons there. 2s2, there's 2s. If I put 2 electrons into it, they would go up and down. It's hard to screw up on an s orbital, right? Because you can't be wrong when there's only one orbital. How are you gonna be unfair? Just put 2 in there and you're done. And then for 2p2, we would go ahead and put in the orbitals. Here's the 2p orbitals. 1, 2, 3 of them in a set. Always 3 in a set. No matter how many you need, you have to draw the whole set, the whole sublevel. Because look here, we have 2p2. Where do those go? Well, there's one, and there's one. And that's all, right? That's all we've got. 2 electrons here means we've got 1, 2 electrons there. I've got room for others, but I don't have the electrons in an atom of carbon. There's only those 2p2 electrons. And so carbon's 6 electrons would fit into an orbital diagram like this. Excuse me. You might ask the question students ask all the time, and that's like, why do I need to show this last orbital here? Why do I need to show that if I don't put anything in it? Can I just leave that off? And the answer is definitely not. Okay, the reason you can't leave that off is because what I mentioned earlier with iron, those 2 electrons would actually move around and occupy all 3 of those orbitals at different times. So in the next moment, right, in the next moment, if we have 3 orbitals, we might expect to find that there's an electron here and an electron here. And then the next moment, we might find that there's an electron in the 3rd one and the 1st one. And there's all these different combinations, right? We could expect to find one here and here. And that would still be okay as well. And in fact, any of these drawings would be acceptable for your orbital diagram. As long as you have them spread out and those 2 electrons aren't together, you don't have to go up, up, and then leave a space like the one that was given here in black. You could put those 2 wherever you want, as long as you don't put them together, because that would break Hund's rule. Okay, so you do need to show all of the orbitals in the set, even if 1 or more of them sits empty in your picture, quote unquote empty. It's not truly empty, right? Because electrons move around and they take their turns in those different places. We can put those electrons in whatever orbitals you choose. As long as you're putting them into different orbitals, you're not breaking the rules. Okay. So that's carbon, a relatively simple example. And by the way, the first element on the periodic table where Hund's rule can come into play. Because before this, there isn't any electron imbalances to have to deal with. But with carbon, we have those two. And you could screw it up if you put them next to each other in that first orbital, or if you put them together in any one of the three orbitals. You'd make a mistake on that. That would be okay, as I mentioned, that would be okay. We've got a lot of other options. So let's try some examples. Let's take a look at some examples on your assignment. Jump back over here to that. We'll take a look at the practice from the same assignment we were working on before. Okay. This is the next page. So yesterday we were working on electron configurations on this page with the 1s2, 2s2 configurations and so on. We're going to go to the very next page here in your binder, and we're going to look at a few examples just on this one. All right. So for sodium, we're going to look at sodium. I think we'll try to do that one, and we'll try to do nickel, and I think it'll probably be enough. We can probably have a pretty good handle on it at that point. Okay. So for an orbital diagram, it doesn't hurt. You don't have to write out the electron configuration first, but sometimes people like to have that electron configuration sort of near them first. You can do that. You can look at your periodic table. You can write sodium's configuration out if you like. Okay, so for sodium's electron configuration, you can go back over to our little guide if that's helpful, and if you don't need it, feel like you don't have to, that's great. Sodium, we know, sort of sits right here. This is sodium's position in the 3s section of the periodic table, right? That's our sodium. So if I was to write sodium's electron configuration out, ending on that one, I would fill in with electrons in the 1s, that's 1s2. I would fill in with electrons in the 2s sublevel, that's 2s2. I would fill in with electrons in the 2p sublevel, that's 2p6. And then I would fill in with that last electron there as 3s1, all right? So that would be electron configuration for sodium, but that's not what we're going for here. But with that in mind, I'm going to take that, we're going to run with it as our example here. Sometimes people in the first few examples, they like to have that to work from, and we can kind of just follow it along, so it's kind of our guide. So I'm going to bring that over. We're going to use that as kind of a guide for sodium. And we'll work on its orbital diagram now for sodium instead. So what is an orbital diagram going to look like? It's going to have those little spaces with the little arrows in them that we've been looking at in examples from before, or from the slides rather. So for sodium then, for 1s2, I'm going to draw in an s orbital. Oops. A little herky-jerky. Let's try this again. Okay. So for sodium, I'm going to draw an orbital 1s. And remember, s is always a single orbital. Whether it's 1s or 2s or 3s, it's always a single orbital, because a single orbital can include 2 electrons, and that's all s will ever have in its sublevels. So 1s2, I'm going to go ahead and draw in the 2 electrons. That's 1s2 in an orbital diagram form. Okay. What about 2s2? I'll go ahead and write that in a different color so we can kind of contrast what we're doing here. You don't need to use different colors, but I'm going to use that. Again, this is an s orbital, so just like before, an s orbital is going to be a single orbital, and this is 2s. Now, I'm going upwards, you notice. I mentioned earlier we do this in sort of a slight staircase fashion because it reminds us that we're following Aufbau as well. 1s is the lowest energy electrons, 2s are a little higher energy electrons, and so forth as we go through all the different sublevels. You don't have to draw it in a staircase fashion. It's nice to do that, but there isn't always necessarily space, and some people feel like the straightness of these is a little more satisfying. I like to do them in slight staircases if space allows, and hopefully you'll find that you have space there. But it reminds me not only that it's going upwards in terms of energy, but it also sort of helps me separate visually the different sublevels because they're all in their own little sort of step or terrace as we go up this. So I like to do that, but it's up to you. 2s2, I'm going to go ahead and put in 2 electrons. So there's 2s2. So that's 1s2 and 2s2 in orbital form. All right, let's go back to blue then for 2p6. So for 2p6, remember, p is a set of 3 orbitals. We talked about them in being in the x and the y and the z axes. We don't have to worry about labeling those here, but that set that includes 3 orbitals and as many as 6 electrons then, that's how we would draw p. Any p orbital set, any p sublevel would be a set of 3 orbitals like this, whether it's 2p, 3p, 4p, and so on. Always a set of 3. 2p6, to do those 6 electrons, I'm going to put 1 in each. So there's 1, 2, 3, and then go back with the 4, 5, 6. I'm following Hund's rule even as I draw this. I'd like you to do that as well. Okay. That's 2p6. We got those drawn. Let's finish out with 3s1. I'm going to switch that over to red just to kind of alternate here a little bit. So this is 3s, and 3s then is another s, so it's going to be a single orbital rather in the set. I'm going to label that as 3s. And how many electrons are in it? Just the one. So that 3s1 is going to come down and show up here as a single electron in that 3s. There isn't another electron next to it, right? This isn't magnesium. If I were drawing the orbital diagram for magnesium that we started yesterday's video with, or the previous video with, we would put a second electron in there, and it would look exactly like sodium, except it would have 2 arrows in that last orbital. But because sodium has only a 3s1, we would leave that second space empty. So there isn't, and you don't need to mark it, but there is no electron in that little space right there. We're going to leave that vacant. There isn't one there. So we would call this an unpaired electron at the end of the sodium configuration. There's an unpaired electron in sodium. So sodium, we said, has 11. I don't think I mentioned it, but sodium has 11 electrons. Let's try that again without a highlighter. Sodium has 11 electrons. Do we have all 11 of sodium's electrons here? Yeah, if we go through and count the arrows, we got them. 2, 4, 6, 8, 10, and one more makes 11. That's an orbital diagram for sodium. All right, let's take a look at nickel. Now, I'm going to try to do nickel's orbital diagram here without writing the electron configuration first. I'm not going to write this form for nickel first. We're going to go ahead and just go right to the orbital diagram. If you feel more comfortable writing it out first, go for it. Keep your periodic table nearby. Keep one of those little guideline kind of fill in the blankers that we've been using, those little pictures. Keep one of those handy if you'd like to, and feel free to take this at your own speed if you want to go a little slower. But I'm going to work through nickels, just going right to drawing the orbital diagram. All right. I do want to know for sure though that nickel ends. All right, make sure we know that where nickel ends, because we want to make sure we don't keep going too far. Right, going for a road trip, and pretty soon you end up 2 states too far. So in the case of nickel here, nickel would be right here on my periodic table. And so it's nice to know, like with the idea I mentioned in the previous video about where the flag is on your golf hole. Nickel's here. And if I had to describe where nickel is, we should know that nickel's going to end, ... bunch of stuff. Nickel's going to end on 3D, right? That's the last sublevel that nickel has occupied with electrons. And specifically, nickel's in the 1, 2, 3, 4, 5, 6, 7, 8th position of 3D. So it's going to end on 3D8. Now, again, you don't need to fill those in or X those out, but you should be able to look at your own periodic table even and just count across to nickel and know that nickel ends on 3D8. That's going to help you know when to quit and know when this thing should end so that you don't go too far. So I'm just going to keep in mind nickel ends on 3D8, and then we're going to go back over here and go ahead and draw nickels out. All right, so let's do nickel. Nickel's going to start with 1s, just like everybody does. There's 1s2. And then it has electrons in 2s, and that's 2s2. And everything's going to be full on an orbital diagram until you get to the very end, and then maybe it won't be full. We saw with sodium that the last part wasn't quite full, right? Only half full. We had an unpaired electron. Nickel is going to be ending on 3d8, so that's not going to be quite full either since D can hold 10. But let's not worry too much about that until we get there. So here's 2p. 2p can include as many as 6 electrons, and just like in the sodium atom above, it does have 6 for nickel. 2p, 1, 2, 3, 4, 5, 6. So there's 2p6 for nickel. What comes next? 3s, just like in sodium, but we're going to keep on filling that up all the way since nickel has a total of 28 electrons. 3s is going to be full, and then I continue on, 3p. As I mentioned earlier, anytime we use p as a sublevel, it's going to have 3 orbitals in it. So there's a set of 3p orbitals that make up our sublevel 3p. 1, 2, 3, 4, 5, 6. There's 3p6. Now we're getting closer to the end, but let's keep on moving here. Keep her moving, like my boy Charlie Barons likes to say. If you haven't watched Charlie Barons videos online, they're funny as can be. Okay, 3p6. And then 4s comes next, right? We're back at the beginning of that next row. 4s2. And again, notice here we've had 1s, 2s, 3s, and 4s. And every time it's just one little orbital with as many as 2 electrons in it. We've had 2p and 3p. And every time it's 3 orbitals with as many as 6 electrons in it, anytime we do p. Now, well, for the first time, we're on to d. And so we're ending on 3d8, though. Remember that d, and I'm going to switch colors just to make it pop a little. Remember that a D sublevel, 3D, 4D, 5D, or 6D, will always include 5 orbitals. a set of 5 orbitals that can each include as many as 2 electrons for that total of 10 that we expect with D when it's full. So there's a 3D sublevel including a set of 5 3D orbitals, each of which can include 2 electrons. So 2, 4, 6, 8, 10 for maximum capacity. We only have 8. Remember, we're going to end on 8. So I'm going to go through and use Hund's rule. I can't go 2 for you, 2 for you, 2 for you, and 2 for you, and then leave the last one empty, right? That would violate Hund's rule. So for 3D8, I'm going to go 1, 2, 3, 4, 5. Everybody gets one first. All right, every orbital gets 1 electron in it first. Electrons, and again, this isn't rules, I want to mention too. The reason that we know this makes sense to us too is that all electrons are negatively charged, right? And so negative charges would repel each other. They wouldn't attract each other. Opposites attract, but like charges repel. And so negative electrons would repel each other. And so they almost like spread out into their own orbitals. They repel each other into their own geometries. And so they aren't going to squeeze in next to each other when there's room in other orbitals. They're each going to take their own orbital because they repel each other. They want to get as far apart from each other. I shouldn't say want. They tend to get as far apart from each other as they possibly can. And that means everybody in their own orbital. But that's only 5. So what about those last 3? You can put them in wherever you want. 6, 7, 8. You could put them in any 3 of those 5 orbitals that each had 1 electron already. And this would represent 3D8. Notice we do have 2 positions left. We have 2 that are unfilled. But remember that in nickel atom, those 8 electrons would sort of randomly just sort of move around within those 5 orbitals. And in a given moment, they would be in any different places at any different instant. Electrons are sort of on the constant move in ways we don't fully understand. So this is nickel's orbital filling diagram. Now you might have to, for some of the larger elements, you might have to draw a little smaller. You might find yourself bleeding across the line here. If you have a longer one and you need to cross over the line into that Lewis dot diagram section that we still are saving for our next video, that's okay. Don't feel like you can't cross the line. You'll have room for the Lewis dot diagrams. They're very, very small. You need about as much room as the size of your thumbnail, okay, to draw a Lewis dot diagram. They're very compact. So feel free, if they're too big, to bleed across that line. You don't have to stay on the left side of that line. But do your best to be neat and do your best to show the staircase. So this is nickel's orbital diagram. What I'd like you to do is try the rest of them on this page. I will mention that there are some big ugly ones toward the bottom. Neodymium, I think, is the only real big ugly one, because neodymium gets us way down into the F block. Chances are that even if you write small and neat, you're not going to perhaps be able to fit neodymium on there, but you can sure give it a try, okay, if you want to. All right. All the rest of those orbital diagrams, again, save the Lewis dot diagrams for now, and we'll work with those another time. We'll work on the rest of those orbital diagrams and then get your picture uploaded into your assignment for me, and we'll take a look at it from there. Thanks for following along. If you have questions, catch me in saber time, and we'll try to straighten you out. In the meantime, have a great rest of your day, and we'll talk to you soon.